From a DML perspective, SQL foresees 4 constructs. The select construct allows to retrieve data from the relational database. The update and insert constructs allow to modify and add data. Finally, the delete construct allows to remove data. In what follows, we will zoom into each of these separately. We start with the SQL select construct. You can see the full syntax illustrated here. By using the options listed, we can ask very specific and complex questions to the database. Let's elaborate more on this. As already mentioned, the select construct allows to retrieve data from the database. It is important to note that the result of an SQL select statement is a multiset and not a set. Remember, in a set, there are no duplicates and the elements are not ordered. In a multiset, the elements are also not ordered. However, there can be duplicate elements in a multiset. You can see this illustrated here. We have a set 10, 5, and 20, and a multiset 10, 5, 10, 20, 5, and 10, where the elements 5 and 10 each occur multiple times. In other words, SQL will not automatically eliminate duplicates in the result. There are various reasons for this. Duplicate elimination is an expensive operation. The user may also want to see duplicate tuples in the query result. Duplicates may also be considered by aggregate functions, as we will illustrate later. In what follows, we will discuss simple queries, queries with aggregate functions, queries with group by having, queries with order by, join queries, nested queries, correlated queries, queries with all any, queries with exists, queries with subqueries in select from, and queries with set operations. Let's get started. Simple queries are SQL statements that retrieve data from only one table. In other words, the from component in the select instruction contains only one table name. The select component then extracts the columns required. It can contain various expressions which generally refer to the names of the columns we want to manipulate. Let's give some examples. Here you can see our first select query. It reads, select subnumber, subname, subaddress, subcity, substatus from supplier. This query selects all information from the supplier table. In other words, it provides a complete table dump. In case all columns of a table are requested, SQL provides a handy shortcut notation, which is select star from supplier. It is also possible to select only a few columns, as you can see illustrated. This query selects the supplier number and supplier name from the supplier table. Here you can see two more queries. The first query selects the supplier number from the purchase order table. Since a supplier can have multiple purchase orders outstanding, the same supplier number can appear multiple times in the result, as you can see illustrated. Remember, the result of an SQL query is a multiset. That's why we see supplier numbers 32 and 37 appear multiple times. The second query adds the distinct option. This option removes duplicates and makes sure that only distinct values are shown in the result. This query shows that we can also include simple arithmetic expressions in the select component. It selects the supplier number, product number, and delivery period divided by 30 from the supplies table. Remember, the delivery period was expressed in days, so if we divide it by 30, we can approximate it in terms of months. Note that we also added month deliv period as an alias or shortcut name to the calculation. The SQL queries we discussed thus far only included a select and from component. A missing where clause indicates no condition on tuple selection. When a where clause is added to the SQL statement, it specifies selection conditions to indicate which table rows should be selected. A number of operators can be used in the where clause, such as comparison operators, Boolean operators, the between operator, the in operator, the like operator, and the null operator. Let's illustrate this with some examples. The first query selects the supplier number and supplier name from the supplier table of all suppliers living in San Francisco. The second query selects the supplier number and supplier name from the supplier table of all suppliers living in San Francisco and whose status is higher than 80. Note that both predicates are combined with a Boolean AND operator. The third query selects the supplier number and supplier name from the supplier table of all suppliers whose status is between 70 and 80. Here you can see some more simple queries. Remember, simple queries only retrieve information from one table. The first query selects the product number and product name of all products whose product type is either white or sparkling. Note the use of the in operator, whereby the strings white and sparkling are combined into a set. The second query illustrates the use of the percentage sign as a wildcard representing 0 or more characters. Another popular wildcard is the underscore, which is a substitute for a single character. In our example, we select the product number and product name of all products having the string short as part of their product names. Obviously, this will select all the Chardonnay wines, as you can see. The third query selects the supplier number and supplier name of all suppliers whose status is null. Several expressions can be specified in the select clause. These may also include aggregate functions used to summarize information from database tuples. Popular examples are count, min-max, sum, average, standard deviation, and variance. Let's work out some examples. The query select count star from supplies where prod number equals 0178 selects the number of tuples in the supplies table where the product number equals 178. In our example, the result of this query will be 5. The second query selects the number of not null purchase values in the supplies table for tuples where the product number equals 178. The result will be 4, referring to the values 16.99, 17.99, 16.99, and 18. Note that the value 16.99 is counted twice here. If we want to filter out duplicates, then we can add the keyword distinct to the query, which will obviously result in the value 3. The query select product number sum quantity as sum orders from PO line where product number equals 178 selects the product number and sum of the quantities of all PO line tuples of which the product number equals 178. The result of this sum is 9, which equals 3 plus 6, as you can see illustrated. The query select some quantity as total orders from PO line simply adds up all the quantities of the PO line table, which results in 173. Here you can see some more examples of using aggregate functions. The first query selects the product number and average purchase price from the supplies table for all tuples where the product number equals 178. The result of this query is a weighted average price, since duplicates will not be filtered out in the calculation. More specifically, since supplier number 37 and 69 both adopt a price of 16.99, this price will be counted twice, resulting into a weighted average price of 16.99 plus 17.99 plus 16.99 plus 18 divided by 4, or 17.4925. In case we are interested in an unweighted average, then we need to add the distinct option, as you can see in the second query. Here, the value 16.99 will only be counted once, resulting into an average of 16.99 plus 17.99 plus 18 divided by 3, or 17.66. Besides the average, also the variance can be calculated, as you can see here. Remember, the variance represents the average squared deviation from the average. The second query selects the product number, minimum price, and maximum price of all supplies tuples for which the product number equals 178. This results into the values 16.99 and 18, as you can see. Let's now move on and add some more complexity to our queries by using a group by having construct. The idea here is to apply aggregate functions to subgroups of tuples in a table, where each subgroup consists of tuples that have the same value for one or more columns. In other words, by using the group by clause, rows will be grouped when they have the same value for one or more columns. The having clause can then be added to retrieve the values of only those groups that satisfy certain conditions. It can only be used in combination with a group by clause and can also include aggregate functions such as sum, min, max, average, etc. Let's have a look at this query. Select product number from PO line, group by product number, having count star bigger than or equal to 3. Basically, this query retrieves the product numbers with at least 3 outstanding orders. If you look at the PO line table to the left, you will see that both product number 212, depicted by the red tuples, and product number 900, depicted by the blue tuples, satisfy the condition and will thus be reported in the output. Let's provide some more detail about how this query essentially works. The group by product number clause will make groups based upon the product number. You can see those groups represented in the lower right corner. We have a group for product number 212, for product number 178, and so on. The having count star bigger than or equal to 3 clause will count how many tuples are in each group and see whether this is bigger than or equal to 3, in which case the product number will be reported. For the group with product number 212, the having count star will give 3, and since this is bigger than or equal to 3, the product number 212 will be reported. For the group with product number 178, the having count star will result in 2, such that no output will be generated. Here you can see another example. Let's assume we want to retrieve the product numbers of products where the total order quantity exceeds 15. This can again be solved using a group by having construct. More specifically, the SQL query becomes select product number, sum quantity as quantity from PO line, group by product number, having sum quantity bigger than 15. If you look at the table to the left, product number 212, for which the total outstanding quantity is 23, and product number 668, for which the total outstanding quantity is 16, will be output. Here you can again see how this query works. First, groups are made based upon the product number. The having sum quantity bigger than 15 clause then calculates the sum of the quantities within each group, and if this is bigger than 15, the product number and quantity will be reported in the output. SQL allows the user to order the tuples in the result of a query by the values of one or more columns using the order by clause. Each column specified in the select clause can be used for ordering, and you can sort on more than one column. The default sorting mode is ascending. Depending upon the commercial implementations, null values may appear first or last in the sorting. The first query retrieves a list of outstanding purchase orders ordered ascending by date and descending by supplier number. The second query selects the product number, supplier number, and purchase price of all supply tuples where the product number is 178. The result is sorted by purchase price in a descending mode. Note that in this implementation, the null values appear last. Until now, we only discussed simple SQL queries where data was retrieved from only one table. Join queries allow the user to combine or join data from different tables. The from clause then specifies the names of the tables containing the rows we want to join. Additionally, it needs to be stated under which conditions the rows of different tables can be joined. These conditions are included in the where clause. Moreover, as with simple queries, it is possible to specify which columns from which tables should be reported in the end result. In SQL, the same name can be used for two or more columns as long as the columns are in different tables. If this is the case, and the from component of a join query refers to two or more columns with the same name, we must qualify the column name with the table name to prevent ambiguity. This can be done by prefixing the table name to the column name. An SQL join query without a where component corresponds to the Cartesian product of both tables, whereby all possible combinations of rows of both tables are included in the end result. However, this is typically not desired, and join conditions can be specified in the where component to ensure that correct matches are made. Let's assume we have the following question. For every supplier who can supply products, retrieve the supplier's number, name, and status together with the product numbers they can supply and corresponding price. First, we start by listing the tables from which we need information, the supplier and supplies table. In other words, we have two tables now, and we will need to combine or join them in a specific way. The question is, how? Here you can see some example tuples from both tables. Our first attempt to solve the question using an SQL query reads: select r.subnumber, r.subname, r.substatus, s.subnumber, s.prod_number, s.purchaseprice from supplier R, supplies S. Note that we use the shorthand notations R, referring to the supplier table, and S, referring to the supplies table. What is this query essentially doing? Well, since we have no where component, it will make the Cartesian product of both tables by combining every possible tuple from the supplier table with every possible tuple from the supplies table. Obviously, this will result in incorrect matchings. As an example, just look at the second tuple in this table. You can see that supplier number 32, which is Best Wines, from the supplier table, is now combined with supplier number 21 from the supplies table. You can see a lot of other incorrect matchings. This is clearly not what we want. Hence, we should carefully define under which conditions the join can take place by adding a where clause to our SQL join query. Our SQL join query with an additional where clause reads as follows. Select r.subnumber, r.subname, r.substatus, s.prod number, s.purchase price from supplier R supplies S, where r.subnumber equals s.subnumber. In other words, the tuples can only be joined if the supplier numbers are identical. When you now look at the tuples in the result table, you can see that the matchings are correct, with data of supplier number 21 from the supplier table being correctly joined with data of supplier number 21 from the supplies table, and likewise for the other suppliers. Here you can see another syntactically equivalent way of expressing a join SQL query using the inner join construct. Both queries will give identical results. It is also possible to join data from more than two tables. Assume we have the following question. For each supplier with outstanding purchase orders, retrieve supplier number and name, together with the purchase order numbers, their date, and the product numbers, names, and quantities specified in these purchase orders. We can again start by listing all the tables needed. We now need data from four tables: supplier, product, purchase order, and PO line. The primary foreign key relationships are indicated with the colored circles. We will need to use those to specify our join conditions to ensure that correct matchings are made. Here you can see our SQL join query. Again, note the shorthand notation that we use to refer to the tables: R for supplier, PO for purchase order, POL for PO line, and P for product. The where clause specifies all the join conditions. Note that this query is quite intensive in terms of resources, since data from four tables needs to be joined. In SQL, it is possible to join rows that refer to the same table twice. In this case, we should declare alternative table names called aliases. The join condition is then meant to join a table with itself by matching the tuples that satisfy the join condition. Consider the following question. Retrieve all pairs of suppliers who are located in the same city. It is quite obvious that we need data from only one table, supplier. However, we need to join this table with itself to solve the question. More specifically, the SQL query becomes select r1.subname, r2.subname, r1.subcity from supplier R1, supplier R2, where r1.subcity equals r2.subcity, and r1.subnumber strictly less than r2.subnumber. Note that we introduce two aliases, R1 and R2, to refer to the supplier table. The join condition is now based upon matching subcity. However, there's also another condition added, r1.subnumber strictly less than r2.subnumber. What would be the rationale for this? Well, let's have a look. To the left, you can see a dump of both supplier tables, which are obviously identical. If we would omit the condition r.subnumber strictly less than r2.subnumber, if we would omit the condition r1.subnumber strictly less than r2.subnumber, then the query result will also include duplicates, such as deli wines, best wines, ad fundum, best wines, the wine depot, best wines, etc., since all of these have matching values for subsidy. To filter out these meaningless duplicates, we added the condition r1.subnumber strictly less than r2.subnumber. Only one result remains then, best wines and the wine depot, which are both located in San Francisco. Basically, any condition can be added to the joint condition. Consider the following question. Select the names of all suppliers who can supply the product with product number 899. We need data from two tables, supplier and supplies, which should again be joined. The SQL query then becomes select r.subname from supplier R, supplies S, where r.subnumber equals s.subnumber and s.prod number equals 899. The result of it is the wine crate. Here you can see how the query works. Tuples from supplier and supplies are merged based upon matching supplier number. In the next step, the resulting join tuples are further filtered. By only considering those where the product number equals 899. This results into the wine crate as the only tuple satisfying the requirements. Remember, the result of an SQL query is a multiset which may contain duplicates. If we want to eliminate duplicates from the result, we can use the keyword distinct. Assume the following question. Retrieve all the names of the suppliers who can supply at least one type of rosé wine. To answer this question, we need data from three tables, supplier, supplies, and product. In some cases, a supplier can supply more than one type of rosé wine and may thus pop up multiple times in the result. This can be avoided by using the distinct option as in the following query. Select distinct r.subname from supplier R, supplies S, product P, where s.subnumber equals r.subnumber and s.prod number equals p.prod number and p.prod type equals rosé. Here you can see the result of the same query both without and with a distinct option. Since Deli Wines supplies multiple rosé wines, you can see it appearing multiple times in the result of the first query. A join condition can also be combined with any of the earlier SQL constructs we discussed. This allows to build very powerful SQL queries answering complex business questions. Let's consider the following example. Find the product number, name, and total ordered quantity for each product that is specified in a purchase order. We need data from two tables, product and PO line. The SQL query becomes select p.prod number, p.prod name, sum pol.quantity from product P, PO line POL, where p.prod number equals pol.prod number, group by p.prod number. This query will first join both tables based upon corresponding product number. The group by clause will then group the join result by corresponding product number. For each group, the product number, product name, and sum of the order line quantity will be reported. You can see the resulting outcome at the bottom of the slide. Here you can see again the same query illustrated. I highlighted two tuples to demonstrate the calculation. For product number 178, which is Meerdal Chardonnay, highlighted in red, the total quantity is 9, which is the sum of 3 and 6. For product number 212, which is Bilkar Salmon, highlighted in blue, the total quantity is 23, which is the sum of 2, 15, and 6. The joints we have covered thus far are all examples of inner joints. This means that we always require an exact match before a tuple can be reported in the output. An outer join can be used when we want to keep all the tuples of one or both tables in the result of the join, regardless of whether or not they have matching tuples in the other table. Three types of outer joins exist. In a left outer join, each row from the left table is kept in the result, if necessary, completed with null values. In a right outer join, each row from the right table is kept in the result, if necessary, completed with null values. Finally, in a full outer join, each row of both tables is kept in the result, if necessary, completed with null values. Let's work out some examples. Consider the following question. Retrieve number, name, and status of all suppliers, and if applicable, include number and price of the products they can supply. In other words, we want information of all the suppliers, even if they cannot supply any products at all. This can be solved using an outer join between the supplier and supplies table as follows. Select r.subnumber, r.subname, r.substatus, s.prod number, s.purchase price from supplier as r, left outer join, supplies as s, on r.subnumber equals s.subnumber. The left outer join clause indicates that all tuples from the supplier table should be included in the result, even if no match can be found with the supplies table. Let's illustrate this. Here you can see some example tuples from the supplier and supplies table. Let's now run our outer join query between both tables. Take a look at this result. What is striking is the red tuple. This is supplier number 52, or Spirits & Co. This supplier has no corresponding supplies tuples. It could be a new supplier for which no supplies have been entered yet in the database. Because of the left outer join clause, this supplier is now appearing in the end result together with null values for the missing columns of the supplies table. Assume we have the following question. Select all product numbers together with the product name and total ordered quantity, even if there are no outstanding orders for a product at the moment. It is clear that this question can again be answered using an outer join between the table's product and PO line. More specifically, the SQL query becomes select p.prod number, p.prod name, sub pol.quantity as sum, from product as P, left outer join PO line as POL, on p.prod number equals pol.prod number, group by p.prod number. Let's see how it works. First, the product and PO line table are joined using a left outer join based on product number. This means that all products will be included, even if they are not included in any purchase order line. Next, the group by clause will make groups in this join table. For each group, the product number, product name, and sum of the quantity will be reported. You can see the result of this at the bottom of the slide. Note that for product number 199, which is Jacques Solas, the quantity is null. Also, for product number 289, which is Château Saint-Estèphe de Néry, the quantity is null. Both are now included in the end result because of the outer join.